And welcome to the topic of short circuit calculations. Just a quick summary of what short circuit is. We have already discussed that short circuit is basically a scenario where the current flow path is interrupted by an alternate path, which of course has low impedance, and due to this low impedance the system current becomes very high and it is required to cut off the system in this scenario. But since the protection devices take a small amount of time, therefore our equipment must be able to withstand this short amount of current, this high amount of current for a small interval of time, and this is what we refer as the short time rating of an equipment. Now the question is that how do we know that what will be the value of short circuit current, or in other words, what are the parameters that are involved when calculating the short circuit current. So basically this is our topic for today, which is short circuit calculation. So always remember that whenever we are talking about short circuit calculation, we need to have three parameters which are involved in short circuit calculations. So the first one is of course the short circuit current, which we usually refer as ISC, right? And the second one is the voltage in case of short circuit, and the third one is short circuit power, which we usually refer as MVASC, right? So now coming towards the calculation of short circuit current. So for short circuit current ISC, it is dependent upon the source voltage, that is what we refer as the pre-fault voltage, and all the impedance from the source up to the fault point, that is the Thevenin impedance from the point where the fault has occurred, from the source up to the point where the fault has occurred. The equivalent impedance between these 2 points is basically the determining factor of short circuit current, right? So what we are saying that the short circuit current ISC is equals V divided by XF, where XF is the impedance up to the fault point. Let's write it here. XF is the impedance from source up to the fault point, which we also refer as the Thevenin impedance, right? Now we know that XF, this is the fault impedance, we can represent it as a function of Thevenin impedance, we can represent it as a function of total system impedance, right? Basically here what we are talking about, that we know percentage XF is equals to XF divided by XT times 100%, where XT is the total system reactance and XF is the fault reactance. So now we know that we can write this XF, this is which is the normal system impedance, as the ratio of what? The voltage divided by the full load current. In other words, we can write this percentage fault reactance as XF divided by V divided by IFL times 100%, and when we rearrange the denominator, this will become XF times I full load divided by V times 100%. Okay, and now what we can say, that we can rearrange this expression to find out the value of XF. So here XF will be equals to percentage of XF times V, which is the voltage, divided by 100 times the full load current. Now let's put this value of XF in this equation. The main equation, which we are referring as equation 1. So now equation 1 becomes I short circuit is equals to V divided by percentage XF V over 100 I full load current, which can be simplified as I full load current divided by percentage XF divided by 100 times I full load. Or we can rearrange it as the short circuit current is in actual equals to the full load current divided by the percentage reactance times 100. So this is basically the final expression for short circuit current, and always remember that in this expression we have not included the fault resistance or reactance. Basically this expression is in the form of reactance. Here you can see, given that it is derived considering that the resistance in the system is negligible. If you have the resistance in the system also, then in all these places we will be using the value of ZF, and Z we know is equals to the square root of sum of squares of resistance and reactance. That is what you can say, that if we are using Z, then Z is equals to under root of R square plus X square, right? And if there is a non-bolted fault, which means that this fault involves fault impedance, then what we need to do, we need to include the fault impedance here as well, right? The fault impedance needs to be added in this total impedance or reactance, whatever we are considering, so that we can find the value of current. If we are asked to find the maximum value of current, we know that it occurs when the impedance is minimum. So in this scenario, if we are asked to calculate the maximum value of current, so we will be considering zero fault impedance as we have done in this calculation. Now the next thing that next parameter in fact we need to calculate is the short circuit power. Number 2, MVA SC. So we know that in case of a short circuit, the resistance is either very low or 0, which means that the voltage at that point would be very small. So the idea is we consider the pre-fault voltage, the voltage that was present in the system just before the occurrence of fault. So now the short circuit MVA-SC is basically the product of normal system voltage and the short circuit current. That is what we call as the pre-fault voltage times the post-fault current. This product is referred as the short circuit power. Now we already know from the previous calculation that the short circuit current ISC is equals to I full load divided by percentage of XF times 100. So what we can call it as equation 2, and then we say that okay, let's multiply equation 2 by root 3 times of VL. So multiplying equation 2 by root 3 times of VL, that is the line voltage. So now it will become root 3 V ISC equals root 3 IFL VL divided by percentage XF times 100. And then what we do is, in order to make this in terms of MVA, we divide it by 10 is to power 6. We divide both sides by 10 is to power 6. So now our expression will become MVASC. Why? Because under root 3 times voltage times the short circuit current, this is equals to the short circuit power, and since we have divided it by 10 to the power 6, so this becomes MVSC is equals to under root 3 IFL times VL divided by percentage XF times 10 is to power 6 times 100. Now another thing that we need to check here is that this thing, under root 3 normal voltage times short circuit full load current divided by 10 is to power 6. This, from the per unit analysis, we know is equals to the base MVA. So this expression can be simplified as MVASC, that is the short circuit power is equals to base power in MVA, sorry, this is nothing, divided by the fault reactance or the impedance from the source up to the fault point times 100. I hope that this is clear now. So now let's start with the numerical of short circuit analysis. This question, I am just reading it out. It says the figure shows a single line diagram for a 3-phase power system. The percentage reactance of each generator is based on its own capacity. Find the short circuit current that will flow into in case of a complete short circuit at point F. Right? So we have this question number 1. In summary, what is asked here is to find out the short circuit current. Find the short circuit current for a bolted fault at point F, right? This is and the figure is also given here. The important thing is that the ratings of reactances in terms of MV, in terms of per unit, are with respect to the generator's own rating, which means there is not a common base so far. This is 12,000 volts bus. Generator 1 is 15,000 kVA with a percentage reactance of 30%, and generator 2 is of rating 20,000 kVA with a percentage reactance of 50%, right? X equals to this, and the fault is given at point F. Now the very first thing that you need to do, you can see that this system is not expressed in terms of a common base. And in order to solve for the short circuit current, we need to have the per unit values expressed with respect to a common base. So the very first thing we need to do is to select a common base. So let's say I am selecting a common base of 35,000 kVA. This is up to you. You can select any common base. There is no restriction in this, right? So now x1 new, I'm saying this, taking this generator as G1, this one as G2. So the x1 new will now be equal to x1 old times kVA new divided by kVA old, and then we have a factor of voltage also, but since the base voltage for both these generators is same, so this factor will become 1, so I am not considering it, just write it as 1 square. So this will become 30% times 35,000 divided by 15,000, so this would be equal to 0.7 or 70%, right? Similarly, x2 new will be equals to 50% times 35,000 divided by 20,000, right? 50% times 35,000 divided by 20,000, and this will be equals to 87.5% or 0.875%, right? 87.5% or 0.875 per unit, right? And now we need to do what? We need to draw the equivalent circuit for this figure. So what will be the equivalent circuit for this figure? Or we can say what will be the reactance diagram for this figure. This is the fault point, right? This is generator 1 reactance. This will be ground from 1. Resistance is not given, so we will be ignoring it. And this is x2. Basically this is the fault point, point F. So x1 and x2, and here we can see that since this is a common ground bus, now what will be the value of short circuit current here in this scenario? This will be base divided by under root 3, base divided by the percent reactance, and for that we need to find the percentage reactance first. So the fault reactance xf equals to x1 parallel to x2. So we can write it as x1 times x2 divided by x1 plus x2, which will be 87.5 times 70 times 87.5 plus 70, so it would be equal to 38.89%, right? Next we need to calculate the full load current, and the formula of power, we know that S base is equals to under root 3 VL times IL. So from here we can find IL as S base divided by under root 3 times of VL. We have S base as 35,000 kVA, right, divided by under root 3 times voltage, which is 12,000 volts. So this will be equal to 1683 amperes, right? And now what we can do is find out easily, we can in fact find out the value of short circuit current. We know that the short circuit current is equals to this formula we have already studied, that the short circuit current ISC is equals to I full load divided by percentage of XF times 100. So this would be 1683 divided by 38.89 times 100. So the short circuit current at for a fault at point A is equals to 4.3. For a fault at point F, this short circuit is equals to 4.32 kilo amperes. Now this short circuit is very important. Why? Because this bus bar should be able to withstand this value of short circuit current 4.32 kilo amperes, otherwise it will get broken. Alright students, let's continue with one more example of short circuit analysis. It says, the question says, I'm just reading out the question, I will not be writing the whole statement here. The plant capacity of a 3-phase operating station consists of two 10,000 kVA generators, each of reactance 12%, and one 5,000 kVA generator, each of reactance 18%. The generators are connected to the station bus bar, from which load is dispatched through three 5,000 kVA step-up transformers, each having a reactance of 5%. Determine the maximum fault MVA which the circuit breakers on LV and HV sides of the transformers have to deal with. Now let's first draw the diagram. So we have first generator G1, whose reactance is 12% and the rating is 10,000 kVA, or we can also write it as 10 MVA. Then we have the second generator whose rating is also 10,000 kVA and its reactance is again 12%. And finally we have the third generator for which the rating is 5,000 kVA and the reactance is 18%, and all of these generators are connected to a common bus bar, which we are referring as the station bus bar. Okay, so now the load is dispatched from this station through three transformers, right? So we have transformer 1, then we have transformer 2, and finally we have transformer 3, right? and these are all step-up transformers. So the question asks that what will happen if a fault occurs at the LV site, that is if a fault occurs at F1 and if a fault occurs at F2. So basically we need to find the short circuit power. This is question number 2, and it's say what we need to find. We need to find the MVASC for fault at F1 and for a fault at F2, right? So the formula is, we know that MVSC equals what? Base MVA divided by percentage of XF times 100. Now for a fault, first we need to do what? We need to select a common base MVA, and since we have two generators of the same rating, sorry, I haven't written down the rating of transformers. Every transformer is of 5000 kV, and reactance is 5%. All of them have the same rating, that is T1, T2 and T3. So now we need to convert these reactances for T1 and T2. So we know that the formula is that X new equals X old times kVA new divided by kVA old times voltage, ratio of voltage also, but since the voltage is same here, so that would be 1. So this means that X1 Xg1 equals Xg2 is equals to 12%. This will remain the same, right? X of G3 will be 18% times 10,000. I'm taking base kVA, that is the base power as 10,000, right? 5,000 equals to 36%. Just let me mention here. Base MVA, I am assuming it to be equals to 10,000 kVA. Again, you can select any different value. This is up to you. There will be no impact on the final answer. So now, whenever a fault occurs at point F1, we need to find out the short circuit power, and for F2 also we need to find out the short circuit power. Let's calculate the reactances for transformers also. Xt1 equals to Xt2 equals to Xt3 equals 5% times 10,000 divided by 5,000 equals to 10%, right? Now for F1, let's draw the equivalent circuit. Now if a fault occurs at F1, all the current will be flowing from generator to F1, generator 1 to F1, generator 2 to this point, and from generator 3 to this point, right? So this means that the equivalent circuit will be comprising of all the three reactances X1, X2 and X3 in parallel, and this is the point Xg1, Xg2 and Xg3. So this means what? That XF equals 1, the equivalent of XF, or we can say that 1 upon XF equals 1 over xg1 plus 1 over xg2 plus 1 over xg3. So this means that when we simplify it, XF will now be equal to 5.14%. And once we know this value of XF, what we can do is put it directly in this formula. Let's name it as equation 1. So equation 1 will now be equal to MVASC equals to base MVA, which we already know is 10,000, divided by 5.14% times 100. This means that the short circuit power here is 194.55 MVA. Okay. Now, when a fault occurs at point F2, let me draw the current flow first. The current from G1 will be flowing through F2 to F2, from G2 also, and from G3 also. Now you can see that once the current is on this common bus bar, the plant station, the only impedances that will be included is T1 if the fault is at F2. Why? Because these two are high impedance paths and the current will not be flowing through this path. All the current will be flowing from the generator up to this low impedance path at F2. So in this scenario, the equivalent circuit would be of this shape, F2. This is, let's call it as the ground, xg1, xg2, xg3, right? And then we will have xt1 only, no t2 and t3, because in case of fault at f2 there will be no current through these. This means what? Now xf in this scenario would be the parallel combination of xg1, g2 and t3 plus xt1. Why? Because these two are in series, these two branches, that is the parallel combination of xg1, g2 and g3 and xt1 are in series. So now we can calculate the percentage xf as 1 over 1 xg1 plus 1 xg2 plus 1 xg3 plus xt1. When we solve it, this will give us 15.142%, and hence equation 1 will give us MVASC as 10,000 divided by 15.14, and since this is kVA, we need to add 10 to the power 3 also, times 100. So this would be equal to 66.05 MVA, right? We are already dividing it by 10 to the power minus 6 in order to convert it into MVA, right? So this would be the short circuit power in this scenario, 66.05 MVA. So I hope that this is clear, and you can see that since one impedance got added here, in this scenario. So the short circuit power has decreased. At on LV side it is 194.55, on HV side it is 66.05. So I hope that it is clear now. We will do a few more examples in the next section.